Welcome everyone. I would really like to, welcome our guest today, Dr. Kevin Mitchell, who is from the Trinity College, Dublin, and he's a professor in developmental genetics and neuroscience. I think I practiced this yesterday already. So the reason why Kevin is in Budapest because we invited as part of the CHARM EU collaboration, where ELTE is and both Trinity and ELTE are part. To give a series of lectures, and we thought that this one will be particularly interesting for a wider audience, as it's about free will. So it's not only a biological or genetic subject; it's more like bridging multiple things. And Kevin is really a master in building bridges in many ways. He already tried to build bridges between the developmental genetics and neuroscience communities, but I think this is an even braver undertaking. Trying to bridge philosophy and neuroscience and genetics. So I'm really excited to have Kevin here. Thank you for coming. And without further ado, please.
Thank you. Well, thanks very much, Mate, for the invitation. It's great to be here. Beautiful setting, and to have a chance to talk about this interest of mine in free will. And actually, a lot of this one is going to be about physics. So this was even a bridge further for me. So the problem of free will is an age-old one, the question of whether we're really in control of our actions, whether we really make decisions. And the you part there, do you really make decisions, is for me actually the hardest, trickiest part of this question. So really the problem of the self. What does it mean to be you, to be a person or a living organism? And how could something that's happening in the world, in the physical universe, be up to you as a holistic entity, not just some sort of a machine? And the point there is that for us to be free, we have to be a self, but we also have to be not pushed around by forces outside us. That's a sort of an obvious criterion for freedom. But the less obvious one that's also really important is that you're not pushed around by stuff that's happening inside you. You're not just made to act in certain ways because your brain circuits are firing in a certain way, or your biochemistry is happening a certain way. So there has to be some sense in which you as a whole agent are in control, even though stuff is happening within you, but you have to have the capacity to do something. And it's not obvious how we can get to a point where a holistic entity can be said to have the power to do things. And really one of the major challenges, there's challenges from psychology, there's challenges from neuroscience and so on, but one of the major challenges, the really fundamental one, is a challenge from physics, which is just to say we're physical beings in a physical universe, we're made up of atoms and molecules and so on, they should be subject to the laws of physics, so how could we decide what goes on inside us? Isn't everything just going to evolve according to the laws of physics? And that's a very ancient idea, starting with people like Democritus, an ancient Greek philosopher who was one of the first atomists, person who proposed that everything in the universe is actually composed of atoms, but he also proposed that they follow predetermined paths. So whatever is going to happen is just going to happen necessarily. And one of his, another philosopher who came along somewhat after him, Epicurus, noted the problem with this idea. If the atoms follow these predetermined paths all the time, there's nothing could ever go any other way, then there's no opportunity for free will. There's no freedom in the universe, there are no possibilities in the universe, and there's no opportunity for control of what happens. Everything would just be determined by the micro causes within the physics. And so actually he reasoned backwards and said, well, clearly we do have free will. It looks like we really do make choices. Therefore, Democritus must have the physics wrong. Physics must not be like that. And I think that's actually a perfectly good, valid argument to make, just taking the evidence that we do in fact make decisions at face value and then saying if your physics tells you that's not possible, then there's something wrong with your physics. So nevertheless, here we are 2,500 years later, and people are still having this same argument. So the free will debate is often just presented as if it's a debate between free will and determinism. Those are the two options. And determinism can be stated like this. So here's two contemporary philosophers, Greg Caruso and the recently departed Daniel Dennett. who defined determinism as the thesis that facts about the remote past, in conjunction with the laws of nature, entail there is only one future. Only one unique future is possible. Now, these two disagree about the implications of that, but they agree on the premise. They agree that this is the starting point for the debate. Greg Caruso ends up by saying, well, if that's true, then free will can't be real, so he's a free will skeptic. Daniel Dennett was a proponent of what's called compatibilism, the idea that, yes, determinism is true, but our ideas of free will, and especially of moral responsibility, can be compatible with the lack of true opportunities at a physical sense. I've never understood how that is supposed to square, and I don't buy it. But well, the good news is you don't have to actually make that move, because it turns out determinism isn't true, so that's good. Many physicists have said this as well. So here's a quote from Stephen Hawking saying that biological processes are governed by the laws of physics and chemistry and therefore are as determined as the orbits of the planets. So it seems we're no more than biological machines, and free will is just an illusion. So this is a very, very persistent idea out there, this premise that determinism just holds. Physics has shown this to be the case. Therefore, we've got a problem to explain how free will could exist. And I just reject that premise altogether. It's a problem not just for free will in humans, it's a problem for any kind of agency, how any organism could be said to do anything as a locus of causal power, as a whole thing, as opposed to just stuff happening within it, because one of the implications of physical predeterminism is causal reductionism. All of the causes are at the bottom. There's no room for anything else. All the causation is exhausted at that lowest level because it's deterministic. So whatever's going to happen at that lowest level is it. That's the whole story. There's no room for any kind of higher order causation to be in play. And that, for me, is really the core of the problem for trying to understand how a whole organism could be a cause of things, as opposed to just events happening within it. So another way to state the idea of physical determinism is that the state of a system at one given time, call it time t, exhaustively defined, plus the laws of physics, just entails or necessitates the state of the system at time t plus 1. Very simple idea. You've got your state of the system, you run it through the laws, that tells you the next state. Now, the problem with that is that that doesn't just tell you this time, the state at time t plus 1, it tells you at t plus 2, and t plus 3, and t plus infinity, right? And so what you get is actually that everything that has ever happened in the universe, from the Big Bang to me saying this sentence, has been completely entailed by the state at the initial point, right? So that becomes well, it seems absurd on its face, actually, and yet many people still sort of take that actually is real. It doesn't seem like it actually is. And so recently I published a paper with my PhD student, Henry Potter on the left there, and George Ellis, who's a physicist, which was just looking at this evidence, supposed evidence from physics about determinism and its relevance for the free will debate. And basically we say that actually physics doesn't show that the universe is deterministic at all, quite the opposite, in fact. So we don't need to start the free will debate from that position. So there's a couple elements here where the determinism, as I framed it, clearly doesn't hold. And the first one is the idea that you can exhaustively define the state of a system at any time. In fact, even before that, the notion that there is a time t, relativity basically breaks that down. But even if there were, it would still be impossible to define the state of a system with infinite precision at the lowest levels. We know that from quantum mechanics, and we also know that the way that the system evolves at the lowest level doesn't just evolve deterministically, it evolves probabilistically. So the first comes from the Heisenberg uncertainty principle, where it's known that actually you can't define the state of a system with infinite precision, because there are some pairs of variables where as one of them gets more precise, the other one gets less precise. And that's just a mathematical truth. It's not a statement about our certainty, it's a statement about the precision in the world itself. So things like position and momentum can't both be infinitely specified. And it's not about observation. They can't both be infinitely precise at the same time, just mathematically because of the way they're related to each other. And then the other is the Schrödinger equation. So the Schrödinger equation describes how the what's called the wave function of some physical system will evolve through time. The wave function is a quantum mechanical description of the complete state of a system. And it looks like it evolves deterministically through time, but only until you look at it or something happens. There's some kind of interaction, at which time what looks like a probability function collapses to one actuality. And it does that apparently randomly, according to those probabilities. So it's just not the case that at the quantum level, things are actually deterministic. Now, most people accept that. Most philosophers and physicists just accept, yes, quantum mechanics is really, really indeterministic at a fundamental level that's nothing to do with observers. It's just the way that the world actually is. But many of them will make something like this kind of a move, which is to say, okay, yeah, quantum mechanics is indeterministic, but classical physics is deterministic. We just know that classical physics is deterministic. And there's a variety of moves that people make that support this idea that we can kind of ignore what's going on at the quantum level. We call these Las Vegas arguments, because it's like what happens in the quantum realm stays in the quantum realm. One of them is about this idea called decoherence. So this is a little tricky, but one of the weird aspects of quantum systems is that they can be in a superposition. That means they have a certain probability, like an electron has a certain probability of being here or here, and until it interacts with something, that it's in a superposition, and then when it interacts, it collapses into one of those, right? And quantum decoherence is the idea that when you have a system with lots of electrons or particles or things like that, they become entangled with each other in such a way that the macroscopic system doesn't show weird superpositions. Right? So you don't, at the level of cats and cars and things like that, you know, your cat's not both here and there until you look at it. It's really, really physically located. Right? And many people sort of take this idea to think that, okay, well, all the quantum weirdness disappears when systems get big enough or they have enough elements. But actually, the weirdness is still there. Like, there's still wave functions, they're still evolving, they're still collapsing, there's still new wave functions coming along. There's just still ongoing randomness all the time. It's not like things stop having a quantum reality once they get big enough. It's just that you don't get really weird things like, yeah, superimposed cats. Okay, so that's one argument that people make, that quantum decoherence solves the problem. It doesn't. Another argument is simply that we just know that classical physics is deterministic, because we all learn in school about Newton's equations and the fact that you just run the numbers through them, and there's no variability in the equations. They just give you an answer, right? So it turns out that you know, Newton was studying for example, the solar system. The solar system is very obliging in terms of being super simple, right? Because the sun is this massive element, and then planets, and you can almost disregard individual planets, make it like two-body problems. That just isn't the case for most systems, right? Most systems don't behave like that. And in fact, even the solar system itself, once you go far enough in time, the predictions start to break down, and there is some actual potential for randomness, which Newton himself recognized in his work. So the idea that we can just extrapolate from this sort of very simplistic Newtonian systems to everything else just doesn't hold. That's an assumption and an idealization. It's not a result of physics. And one of the issues here is that part of the assumptions that have to be made here is that all of the parameters that describe your system are given with infinite precision all at once. And that's a mathematical idealization of infinite precision of those numbers. It becomes really hard to even think, what does that even mean in physical terms? And in fact, there's good arguments that it's impossible in physical terms for those parameters to be infinitely precise. So even at classical levels, regardless of the quantum weirdness, even just for classical systems, the idea that you can define the state of a system with infinite precision breaks down because of this. So that would mean that any physical part of the universe that you're calling your system would have to have infinite information in it in order to encode the parameters with infinite precision and all of the future states. Right? That would be an infinite amount of information, but there's a real physical limit to how much information you can store in a given quantity of space, because information has to be physical, so it has to have some matter arranged a certain way. That means it has to have a certain energy, and if you put too much energy into a finite space, you create a black hole. So there's a limit called the Bekenstein bound, which is just says you can't have infinite information. within a given part of the universe, or indeed in the whole universe. And that becomes especially interesting because when we think that actually the universe is expanding, so we have this point down here at the Big Bang where the universe is thought to have started, and it was small, and it got bigger fast, right? So the possibility space, the ways in which the matter in it could be organized, is increasing all the time. So we have greater potential entropy, in terms of how things could be organized, but the universe equilibrates more slowly than it's expanding. So the actual state of the universe is not equilibrated, which means there's information is actually being generated as we go along. So the idea that you can have this infinite information doesn't even make sense in an expanding universe because the space of possibilities is not yet even existing. Okay, so all of which is to say that classical physics is not deterministic. It's not a result of classical physics. It's this sort of idealization that makes the mathematics easy. But in fact, the idea that classical physics is deterministic is as this top quote there says, it's a very odd one because there aren't any good arguments for it. And really, it's a sort of making a postulate of wishful thinking. Now, what are the implications then for us? The idea that there's just one timeline, that the future is fixed, seems to go out the window, is not well supported here. And in fact, it looks like something like this is more realistic, that the state of a system at time t, plus the laws of physics, generate a set of possible states at time t plus one of which will be realized, and then you'll have a set of more possible states, and that state space will get wider and wider the further you are from the present time. So the future, in this case, is genuinely open, and possibilities exist in an ontological sense, right? Which seems to be the first thing that we need for free will and for choice, is that there are some options available to us in the physical universe. But that's clearly not enough. We have to ask, well, okay, how does indeterminacy help in terms of control, right? We have some freedom now. The freedom just comes for free in the universe, but where does the control come from? And this is often sort of presented as there's two horns of a dilemma, which are either events are determined at the microscopic level, and therefore what I did was not free because it was just from physics, or some of them are undetermined, but if the undetermined microscopic causes are still the thing that are making me behave in a certain way, then I didn't do them. That was just random events in my brain, and therefore I'm not free. So either way, it feels like you're not a free agent in control of things. And so you can think about the deterministic view like this. You have this kind of sacred timeline here where there's just a single timeline. Nothing can ever be different. In fact, here there's actually no difference between the past and the future in this idea. This is another idea which many people seem to support, but I think it's not a good way of thinking about things. So we call this determinism plus randomness. And the idea here is to say, okay, well, most of the time, the default way that things evolve is deterministically, but every once in a while, some random event happens, and that can push things one way or another. And so here, the random events in that case are like positive intrusions into the universe. They're like an extra thing that's added that disturbs the typically deterministic goings-on. And I think that's just not an accurate way of thinking about it. And this view is very difficult to square with free will, because it suggests that whether you went left or right at one of these red arrows, it was because of the random event that did it, not you. Okay. So I want to present a different idea to that, which is to think of the indeterminacy not as a positive, extra, intruding element, but as a negative. It's just that the way things are underdetermined, the way things could be, based purely on the low-level laws of physics. Many things could happen at any point. Okay? So it's not that the randomness determines what happens, it's that it allows scope for something else to determine what happens. Now, all of the causes don't have to be at the bottom level, because they're not exhausting the potential scope of what happens. So it's the underdetermination of the future by the present state that is the thing that is allowing some scope for agency. And we call that pervasive indefiniteness, for want of a better name, where the idea is that the future is really open. As it gets further away, it's not just open, it's genuinely undefined. There's no truth value to a statement like it will rain a year from now. There's not a yes or no answer to that we just don't know. It literally doesn't have a yes or no answer yet. It just has to wait. The universe has to wait until things happen, at which case it will become defined through time. Now, this question then is, how does the indeterminacy help? Is by opening up some scope, some slack in the system that allows another type of causation to come into play. And this was already proposed by Epicurus, 2,500 years ago, and developed by George Ellis and Helen Stewart and others. And the idea is that the macroscopic organization of a system can constrain what happens. And that can sound like this sort of weird metaphysical idea, this top-down causation. It's sort of mysterious. It's not mysterious at all. It's totally commonplace. That's what's happening in my computer right now. The electrons are being constrained by the way the hardware is set up, by the software that it's running, and by what I want it to be doing as I'm clicking this clicker and so on. And that doesn't override the laws of physics. The electrons are still obeying the laws of physics there. It's just that the possibility space is constrained by the boundary conditions that are set on it. Okay? So the macroscopic organization can have a causal influence precisely because the lower level is not exhaustively causal. And that idea of the power of organization is if you think about causality, I think a lot of the time we think about causes as these physical things that happen. You know, something hits something else and that was a cause. But there's another way to think about causes, which is just the way a system is organized, which can constrain what happens. So you can think, for example, here, you know, the cue ball hitting the pool balls is the cause of them bursting apart. And that's true, but it's not the only cause of what happens, not the full explanation of what happens, because there's also what we call dependence causes, which is to say that the way that the cue balls burst apart depends on lots of conditions that were set in place. For example, that they're made out of marble, so whatever they're made out of, instead of marshmallows or something like that, right? So you could imagine a whole set of conditions that could have pertained or obtained that would have led to a different outcome. Right? So, and also the fact that they're tightly organized in a triangle like that, right? So we can think about these dependence causes in a few ways. One, they're just can be really generic, what something is made out of, just the laws of physics happening to be what they are, the chemistry of carbon or calcium or whatever it is. But there's also more local, more interesting ones. And those can have functional importance. Those are the ones like the way my computer is designed for a reason, and it can be a record of prior history. And that is exactly what makes living things different from other things in the universe, is that they carry their history with them in their own organization that allows them to control what goes on in the world and within themselves. So you can get, especially if you have selection acting continually or iteratively, then you can get organizations that emerge for a purpose. They're for something. And in living things, what they're for to begin with is persistence. So living things are again, here's Schrödinger talking about what we should think of living things as from a physics point of view is that they're an improbable pattern of matter, of chemical processes that resists the second law of thermodynamics that says things should just go to equilibrium with the universe, with their environment. And living things don't, at least for a time. So they sustain themselves, they sustain that pattern. And really you can think about this as saying in a world where many things could happen, organisms make themselves happen. And they just keep making themselves happen. That's just literally what it means to be a living thing, is you keep making that pattern persist through time. You can think about that even at the lowest level of things like bacteria, where this is a sort of little schematic of a little single cell with lots of metabolic processes going on within it. And all of those processes have these feedback loops that maintain the dynamic structure of the whole thing. Keeps an E. coli bacterium being an E. coli through time. Okay. So they have to do work to do that. They have to take in energy, and they take in matter. In fact, the matter is constantly in flux. They're not made out of stuff. They're a pattern. The stuff is going through. It's in transit. So the pattern is the thing that persists. But the problem is that the world is very uncooperative. Right? So the world keeps changing. which means that if an organism is to persist, then it's a good trick if it learns something about what's out in the world and it can adapt and reconfigure itself to adapt to changing conditions. And that's exactly what evolution found as a solution to this problem. So here's our little bacterium, and now it's able to move around in response to things in the world. So, for example, in response to food, if it's running out of food, it can detect food using these chemical receptors on its surface, which get some information, and they convey that information into the internal bits of the cell, and then it has this little outboard motor that it can use to move around. Okay? And the good thing to do, the thing that evolution has taught it should do, is it move towards a food source. But it can detect other things, like dangerous things, and it can move away from them. So it has these approach-avoid options, which are purposive, right? That's goal-directed behavior, even if it's a very simple kind of that. But this really is purpose, this thing that never existed in the physical universe. It doesn't make sense to say that electrons have purpose, or planets, or rocks, or anything like that, but living things do. That's what defines them. Right? We shouldn't be afraid of talking about it because it sounds non-scientific. It's the whole point of being alive, is to stay alive. And what that means is that information now becomes meaningful, and it becomes valuable. Right? We can talk about information. We have an information theory. It's what allows us to build things like computers and so on. We don't have a great theory about meaning, but that's exactly what organisms need to get around in the world. They need to know something is good or bad, I should approach or avoid it. That has value relative to my goal of persisting. Okay? So you can think about that kind of from an engineering point of view, and you could say, well, evolution has wired in these control policies where an organism, if it senses something, right, if A is the case, then do X. So if there's food out there, then move towards it. And you can think that that kind of embodies a pragmatic knowledge about the world where evolution has done the learning, and it's the factory settings already give these policies to the organism. In fact, what happens, of course, is that the organism just doesn't encounter just one thing at a time. It encounters multiple things. So it has to integrate a few different things. There has to be some context to these policies. You need some second-order kind of contextual things where if A is the case and B, but not C, then do X, right? So in this case, you're now getting an agent that's not just a stimulus response machine to isolated stimuli. It's assessing a situation in a more holistic way where you could say it's the organism doing it. It's not just being pushed around by its parts. And I think if you look at the actual biochemistry of this moving towards a food source in bacteria, then these are the components of it. And you can get a kind of a view of it that does look very mechanistic and very reductive, like the organism is just not doing anything. It's a place where things are happening. So if you take this view, you can say, okay, well, here's some molecule outside. It's detected by a protein. That leads to some chemical changes inside it, which ultimately impinge on this motor here and make it move one way or another. Right? So that description is accurate but so limited as to be really, really misleading. It makes it look like the organism is being pushed around by things happening inside it. In the same way that many people make arguments that we're pushed around by events happening within our brains as opposed to us doing things, right? Now you can take a different view if you actually look at what really happens in the real world, because that kind of view that we saw a minute ago is from very controlled experiments where the only thing that is varying in the world is whether there's a food source or not, right? So all the other things that a bacterium might care about have been controlled. Of course, that's not what the world is like at all. The real world is really complex and dynamic. And when you look at in detail at the way that these systems actually work, you see something that's more like this, right? It's integrating multiple things. It's integrating them over time, so its recent past is determining whether it knows it's going up a gradient or down a gradient. All of those things are dependent on the context, like the cell density, its own metabolic state, temperature and osmolarity and so on. So here you get a picture that's really different, right? A picture of an endogenously active entity. It's not just waiting for stimuli to respond to. It's doing stuff all the time, and it's accommodating to new information in the context of it, what its own state is, what its recent history is, what else there is out in the world. And that really becomes what we can call, I think, agentive behavior, right? So the meaning in the system there for the organism is meaning for the organism. It's not for any of its parts. The organism is the locus of concern, and in an evolutionary sense, the locus of fitness, and it's also the locus of causal power. Right? Its parts are not trying to do anything. Its parts don't care about anything, but the organism does, and evolution cares about the survival of the organism, not the survival of its parts, which are being turned over all the time. So that's for like simple things. I mean, even the simplest organisms we know of, I think we can think of as agents to a certain degree. Of course, that gets more sophisticated as we go through evolution. And when we go from single-cell organisms to multicellular organisms, they face the same challenge to survive in a changeable world. They have to figure out what's out there and what should I do about it. So they need some sensors, they need some motors, and they also need a control system between them. And the control system, of course, is the nervous system, which evolved almost as soon as animals evolved. Even just once you get past sponges, you've got things with nervous systems already. And a typical way of thinking about neurons is something like this. So here's a neuron. It has an input side where it gathers some information, and it does some kind of processing of information inside it. And then if it decides to send a signal that travels down the axon, it impinges on some other neurons, and then at these local connections called synapses, you get this detection of neurotransmitter, and that drives another electrical signal. And that's fine. It's not inaccurate, but again, it's a misleading perspective. So it lends itself to this idea of this driving metaphor, where you have some light hits your retina, and that excites your neurons, and that drives information or activity into parts of your brain, and ultimately drives activity of motor things, right? It's still this big sort of stimulus response idea with a driving metaphor, and you can think then of the nervous system as from an electrical engineering point of view, where we're really all robots being driven by these things inside us. But I think there's a way to flip that. I think this has it exactly backwards as to what's really going on, the real causation in the system here, because actually you can think of each neuron as interpreting its input. So they don't only get one input, they get lots of inputs, and they can come with different rates of firing, whether they're coincident or not. Some of them are excitatory, some of them are inhibitory. So each neuron is really doing a kind of a calculus of what's out in the world, its world being other neurons, and what it should do about it, just like a single cell would do. So it's set up with some criteria for what it should respond to. And Peter Tse has talked about this idea of criterial causation. So again, this is a case where we're moving away from the idea of the production causes, the things causing some oomph, and we're focusing our attention instead on the dependence causes. How is the system structured and configured? How did it get that way, and what does that mean? What does that mean that it's actually doing? And the idea is that the neurons have this configuration of their synaptic connections which encodes criteria for firing. Basically, they set the sensitivity of the neuron to specific aspects of its inputs. And those can change, right? First of all, they're a record of evolution. They're a record of past experience through learning that sets those synaptic weights. But they're also a reflection of current state. They're a reflection of top-down constraints. So when you decide to adopt a new goal, that's a top-down constraint, which changes the configuration of other neurons and changes the criteria, what they're going to respond to. And even things like attention and arousal and other issues of mental control are all manifested through this mechanism of changing very rapidly in real time the sensitivity of neurons to the inputs that they're getting, which is where the real causation in the system actually lies. And what I would say is that these are effectively reasons. Right? Organisms do things for reasons. These are the practical, physical manifestations of reasons. That's how the nervous system encodes those. So, like in simple systems, we have these kinds of simple control policies that can be wired in by evolution, and you can wire them into neural circuits just the same as you can wire them into biochemical circuits. So here's an example this is a lamprey, a very simple fish, where you're looking at a section, its head is facing this way, and it has eyes on either side, and it is it has a couple of sort of reflexive actions that are interesting. One, if there's big looming shadows to the side, those are often predators, so that prompts an escape response. But if there's small moving things in its vision in front of it, those are often prey, and it will move towards them. Okay? So you can wire in policies like that, and even ways to adjudicate if there's multiple signals at the same time, which it has to do in different ways here. Okay? So that's powerful, but it's limited because evolution can't anticipate every scenario that an organism will ever face. And instead, what it has done is endowed the organisms themselves with the ability to learn from experience. And that's what neural circuits, of course, are really good for, is for learning. So that gives much greater flexibility and autonomy to the system itself as an individual in figuring out what it should do and being able to control itself. And those systems have emerged by separating signal from action with lots of intervening levels. So this is what happens in our systems. The distance between our sensory organs and our motor actuators is now huge, right? Our brains have gotten more and more complex in the middle. They do lots of internal representation of information, and they don't just immediately have to obligately respond to every single element in the world. Instead, they take in information, get a view of the whole thing, and figure out what's the best thing to do, especially by linking to prior knowledge. What this means is that we can accumulate information about the world that gives us the power to act in a more autonomous way, predicting what's going to happen, right? We're not just anticipating things, we're predicting, or sorry, we're not just reacting to things, we're anticipating and predicting what's going to happen by building up this model of the world and a model of the self based on our learned experience with objects in the world and with events in the world that have happened in the past, right? So all of this allows us to build up a model of causal relations in the world such that when we encounter some scenario, we can make predictions of what might happen. So one way to sort of summarize this is to say that, you know, we have these first steps of perceiving things, we assess an external situation, but we also assess our internal states and our drives and our goals, because we're not just sitting waiting for something to happen, we're busily doing things all the time, right? So we accommodate to some new information, and then there's this process of cognition in which we think about possible actions, we predict what their outcomes might be. We evaluate whether those would be good or bad, and then we sort of have an internal competition that lets us decide between those various options which would be the best one to do based on these predictions, and then that one gets released. So we're acting, and then that's not the end, of course, because we assess the outcome, and then that's used for learning, and that updates the model, reconfigures the weights, and then the next time we perceive something, we take this history with us as a self that continues through time, psychologically. There's lots of neuroscience about how this works. This is a really simplified version where there's these patterns of neural activity which get subjected to this evaluative sort of simulation where past learning is part of the input to that. Internal states and motivations are part of the input that will upvote or downvote these different possibilities, and eventually one of them gets released and sent to the motor command centers. So this is a really, really simple schematic, and one thing you might think looking at that is that the way that the system is configured at any moment kind of necessarily determines what the outcome of those computations is going to be. And some people argue for that. They'll argue for determinism, not at the level of physics, but at the level of neuroscience. Say, okay, whatever happens, those neural circuits are going to run through this algorithm. The weights are kind of preset, basically, and it's going to run through that and spit out one thing where, again, it's like you couldn't really have done otherwise because it was already, in a sense, predetermined. This is a more accurate view, still super, super simplified, of all of the bits of the brain that are involved in decision making, and you can see how nonlinear this is, right? All the feedback loops that are active here, and the idea that this could in any sense be algorithmic, like one step after another, where you just input your new data to the choice machine and it spits out one answer, becomes much less intuitive, I think, when you start to see these kinds of pictures. And of course, the other thing is that these neurons are noisy. They're firing is not deterministic because they're made of atoms and molecules that are themselves indeterministic. So there are lots of fluctuations that are going on. So there's no sense in which you could think the system will run exactly the same way through this whole set of complicated processes, because the physics itself now says that that shouldn't happen. So the idea that at any point when you encounter some scenario, your decision is already determined, becomes much, much less likely under these kinds of scenarios, and there's really no evidence that that's the case. But it comes down to this question, like, when do you think the decision is determined? At time t, when you encounter something, or by the time you have acted? And I would say that at time t, it's not decided what you're going to do most of the time, right? I mean, in some scenarios it effectively is, but in most scenarios it isn't. But that would account to a kind of a predeterminism by your current state. And it would mean that there's no real-time choice. But I think what actually happens is that there's a process of deliberation which involves all of those different brain areas talking to each other, trying to sort of satisfy their own local constraints so that the whole system can adopt a new global state, which is the decision to do something. So the decision gets determined through the processes of cognition. We really have to think about things. It's not preset. The weights are not preset. You have to establish what those should be in any new scenario. How am I doing for time? I forgot to bring in a thing. Okay, so thank you. So let me just give a couple final objections to this idea that we're really in control because we've evolved these kinds of systems to use information to make happen what we want to happen. So some people would say, okay, but that's fine. I'm using the randomness in the world as a get-out clause to get away from real physical causation. But isn't it the case still that I've just said that these neural operations are noisy, which means there's some randomness at play. So if it wasn't determined ahead of time what I would do, nothing about me determined what I would do, then in the course of my deliberation, isn't it the case that the randomness still is pushing me one way or another? There's the randomness that made the choice. So this is there's a kind of objection that's called a luck objection in the philosophical literature. And I think it derives from the idea of this determinism plus randomness. The idea that things would have gone along a certain way, except there were these intrusions, these little burps that edged it off one path onto another, right? If you think about it like those positive things, then it does kind of feel like the luck is driving things. But if you think of it as a negative, right, as just an underdetermination, then you're just saying, well, actually the organism just has noisy machinery to work with. And it's trying its best. And yeah, if you ran that once, again, it might go one way or the other way, but either way, it was the organism doing a decision. It just wasn't predetermined. So you could say, well, okay, well, if you were conflicted between doing A or B, and nothing at time t was a determining factor, then yeah, it's just really luck. But I think that focuses, first of all, on this contrast between doing just A or B, which is usually a super arbitrary, artificial kind of thought experiment. But it also focuses just on the last little bit of whether you did A or B, and it's looking for a difference maker, right? And they say that the reason that you did A versus B was just luck. It went one way or another. But that's not a full explanation of why you did A or did B. There's a whole chain of thinking and so on that's going on with all of your past reasons and all of your current deliberation involved in that. So it's not, looking for some positive thing which is driving the full decision is not actually accurate here, right? The indeterminacy is not a positive difference maker. It's just the absence of complete determinism. So it's this general kind of background condition, and we're still making decisions, or trying to. And we're trying to control what happens. Sometimes we're trying to really, really tightly control. Sometimes it's a bit looser because we have some leeway in what we care about. And there can be randomness at play, within this space here that we have actively defined as part of our decision making. So just focusing on this last little bit here that's within those little lines is, to me, just a conceptual mistake because it ignores all of the elements of decision making that have gone into it. So we just call this the principle of sufficient control, where the idea is that organisms exert control only to the degree that they care about because lots of things in the world they don't really care about. I mean, here I'm waving my hands around. I don't care exactly where my fingers are right now, right? The job of me waving my hands is being accomplished in a generic sense. I don't have to micromanage everything that's going on here, right? And I certainly don't have to micromanage what's going on at the quantum level here, and I couldn't even if I tried, right? So I have a limited control at the macroscopic level to make things happen at the macroscopic level that I care about. And I don't care about the little micro goings-on that are in there. So I don't need to exert control over that, and I couldn't even if I wanted to. Okay, so just to summarize then, we started with physics, and because that's where the free will debate often starts, with the idea that physics just says free will is out the window because everything's deterministic. And in fact, that's not what physics says at all. We just don't have to accept that as a result of physics. It's an idealization that's sometimes useful mathematically, but actually a full sort of survey of current physics really strongly suggests that microscopic indeterminacy is the case, both empirically and theoretically. So that means the future is open. So that's our first job, is to say at least there's some possibilities that organisms can try to navigate. But the really fundamental idea that gets around that shows how indeterminacy can help is that creates this causal slack. It allows macroscopic control and organization to have some causal power in the system because all of the causation is not exhausted at the lowest level. And that just really defines what living organisms are. They just are macroscopic systems that do work to make themselves happen. Right? They're dynamic patterns or regimes of dynamic processes that persist through time by doing work, even though the stuff that they're made out of is in flux. And they have evolved control systems to act in the world to make happen what they want to happen, which is in the service of continuing to make themselves happen. Right? So they want to keep persisting. One good way to keep persisting is to make things in the world the way you want them to be. And evolution has found those design principles and put in play control systems that really are agential. They're not the organism just being pushed around by stuff inside it. They're the organism using its machinery to do what it wants to do. And in humans, of course, those systems are elaborated way beyond what we see even in simpler mammals, to include things like metacognition, for example, where we're not just reasoning, but we can reason about our own reasons. We can adjudicate whether we should have those reasons or not. We can say how certain we should be about thinking about something. We can weigh various bits of information against each other to see if they're consistent with each other. So that gives us a kind of a level of rationality and rational control beyond what we see in a lot of other animals. And that effectively is what I think we refer to when we use the term free will. That's what we're talking about. It's the ability to rationally control our actions and decisions through time. So I will leave it there. I hope I've convinced you, maybe, that free will is a real thing, and that certainly, at least, that physics doesn't rule it out. Thank you. And I'm very happy to take any questions if there are any.
When an individual makes a decision that's completely against its interests, such as taking its own life, so when an individual makes a decision that's completely against its own interests, such as taking its own life, should we consider it as a dysfunction of this model?
Yeah. It's a difficult example. So the example of suicide is really difficult. So I would say usually it's a pathological state, right? So, and I don't consider it as the ultimate exercise of free will. I just consider it as pathology. But there's another example which is a little less fraught, which is the idea of people deciding not to have children. So from an evolutionary point of view, that's equivalent, right? You're deciding to go against all your evolutionary imperatives to pass on your genes. And of course, people do that all the time for lots of reasons, right? To me, that is a better example of real free will, because we do come with evolutionary drives, but we can exercise rational control over them for much, much sort of higher level emergent reasons. You could decide not to do it for the sake of the the ecology of the world, say, something like that, really high level kind of concept idea. And that's where we can use our cognition to drive our own behavior in a way that isn't ruled out by physics or neuroscience or anything like that, right? There's a sense in which there's a kind of a question. It seems mysterious how a thought, something as abstract as concern for the ecosystem of the planet, could cause something to happen. But actually, I would say that kind of mental causation is just happening because all of the neural activity that's going on in your brain has some meaning to it, right? It's a semantic engine. It's not just this electrical machine. Those electrical patterns mean something, and those are the things that we think about it. When we're thinking about it, we're just operating over meaningful patterns of neural activity. And some of those we can prioritize up or down as parameters that we care about in making any given decision. Yeah.
So I'm wondering, like, given your definition of free will, are there any other species besides human that would satisfy this level of cognition?
Yeah, well, so that's a great question. I reserve the term free will for humans not out of any kind of principled reason, just to avoid trouble. So free will, like in the free will debate, generally people refer to humans, and they refer to this, especially this sort of the rational faculty, so that we're not just immediately driven by every kind of low-level emotional impulse or immediate sensation and so on, right? But if you think about the term agency, it's a more less loaded term, right? Then I think that applies to every living organism, actually, but not to the same degree, and not in the same way either. I don't think it's just a continuum of more or less. I think it's different styles of agency, different degrees of autonomy, and so on. Like you could think one dimension would be how far in advance can a creature plan? And we can plan infinitely far in advance if we want to. I mean, we really think about things thousands of years beyond our own lifetime. Most organisms don't do that, but some of them can plan, a day ahead, plan for the winter season by caching food around, that kind of thing like that, right? So that ability to plan over longer time frames, I think, gives greater autonomy, because what you're doing is you're making the farther future happen. Right? And you're actually having to maintain active behavioral control through that process to achieve a long-term goal. You can't just decide to do something and then just sit back and say, I've decided. You have to keep on deciding to keep on doing it, right? So, so I think there's various kinds of dimensions along which you could think about agency where it can manifest in different ways. I think insects may have a different kind of agency to what we have. Bacteria certainly have this very, very minimal proto kind of agency, right? But they're all doing something. Yeah.
So I was wondering from a mathematical point of view, actually, because I'm a mathematician by training, whether the determinism plus randomness argument, which seems very appealing from one point of view, whether it's a real because it's some sort of it's a common misunderstanding of the word randomness, because randomness in mathematical terms is just a distribution. So everything is a distribution, so everything is randomness. But we often use the word randomness in common sense as a way to say that it's out of our control.
Yeah.
And so by saying that it's determinism plus it's out of our control, then it just becomes sort of tautological or circular in a way.
Almost by definition, if you understand it that way, then it rules out free will either.
We mean by that it's determinism plus, say, Brownian motion, because Brownian motion is out of our control. But then the question boils down to your previous question, whether there's top-down influence of a more complex system down to a more kind of basic level. Yeah. And then it becomes the same question.
Yeah, so it's a great question, because the issue of randomness or even like uncertainty, often is conflated with unpredictability. And people will say it's not really uncertain, it's just unpredictable. And even, they talk about like chaotic systems where they have sensitivity to initial conditions, but people will say, but a chaotic system is really deterministic. And I will say, well, no, that's just an assumption that it is. You can get chaotic behavior in a computer that's running a simulation deterministically, but you have to poke it, you have to change the conditions yourself, and then get a different outcome. So you can show sensitivity to initial conditions in a deterministic system. That doesn't mean that you've shown that the system is always deterministic, because if it's a real-world system, then this noisiness can be happening all the time, right? So it's always changing the conditions at every step. And when you said, randomness is a distribution, in this case, the randomness is a draw from the distribution, right? That's the random element. The distribution can exist, and that's exactly what the wave function is. It just is a probability density function. And the collapse, whatever you think about that means in physical terms, is a draw from that distribution. And the draw seems to be really made at random, in that doesn't seem to be anything else, right? There aren't any of these hidden variables that actually exist. We just don't know about them, right? But it's a constant sort of idea in the philosophy of randomness, is whether this is a real thing, whether when you say something's random, it's a statement about the thing, or it's a statement about you and what you know. And I think, here certainly in the paper, here we go through the evidence that it's really actually in physical terms, it's a statement about the universe. It's not a statement about us. It's not about predictability. It's really about the uncertainty being baked in, the indeterminacy being baked in. And then, then the question is, okay, well, if it's not preset what's going to happen, then what does determine what happens in the go of things, right? It's not determined now, but something's going to happen. So some actualities have to emerge from this set of probabilities. And for many systems, like many chaotic systems, if they're sort of left to their own devices, then they could go all over the place. And that manifests by, if you look far enough in the future, then actually the distribution of possible things that you would get here becomes random with respect to the conditions here. Past some point, you could change the conditions here and you'd have the same distribution out here. So if you think about, again, I talked about the weather system will evolve within a set of constraints, within a certain possibility space, but within that, it's just really, really random, beyond a certain time point. We're not like that, right? The challenge, actually, if you just flip this on its head, the challenge for living organisms is like, how do we ever stay organized, given all this turmoil of potential randomness? And we do it because we've evolved to be robust to that. We've evolved systems that channel it and keep it within our operating range of good parameters. But that requires organizational work. That requires design work. Actually, that's what evolution does. That's what computer engineers did. That's why our simulations run deterministically, is because they put all the effort in to make sure that things are constrained to run deterministically. I don't know if that answered your question. It was more of a rant, to be honest. But yeah, the thinking, it's really just a super interesting question when you think about randomness. Like, yeah, sometimes it is that just there's something there that we don't know about, but sometimes that's just not the case. And the two things are different, and it's good to keep an eye on what you think you're talking about and what people have actually given evidence for between those two possibilities. Yeah.
Thank you.
I think following up Martin's question would be, and what about the AI, or would it be getting free will based on the arguments that you use for the animals, or?
Yeah, yeah, that's a big question these days, is whether we could expect artificial systems to be made that have agency. And I think if you look at the kind of design principles that you can work through by looking at biological organisms, especially the way that they evolved, you could think about building a system that takes in information, that learns about things, that has some built-in goals and some purpose, that can adjudicate over multiple possible actions and weigh them up, especially if it has some internal indeterminacy, so that it's really opportunities for holistic causation to emerge, as opposed to this part-driven kind of causation. yeah, I don't see any reason in principle why that couldn't happen. I think absolutely you could build artificial agents that do that. At the moment, like the people making like large language models and things like that, they're not, that won't lead to real agency because they're not trying to build it. Right? Those are not things that intervene on the world. They're not causally interacting with the world in a way that lets them learn about causal relations that they can then use to adapt their behavior to circumstances. But I don't see any reason why you couldn't, with other design ideas, build something that is a real artificial agent. And in fact, I think it's going to happen. I think it's going to happen in virtual agents first, but I think it's going to happen in robotics. I mean, look, we've already got like self-driving cars and stuff like that. It's just a few extra potential layers of adding systems that grant it more autonomy until you would get to a point where, for all practical purposes, the as-if agency that you build in is just indistinguishable from real agency, and then you're just having a semantic argument about whether to call it that or not, but effectively it is an autonomous agent in the world. So yeah, I think that becomes really interesting ethically, practically, about what we're going to do when we're faced with the possibility of creating agents, artificial agents like that. Great. Thank you very much. Thanks all.